Thank you, Edwin. Welcome, everybody. So, yeah, my name is Declan MacDonald. I'm a technical superintendent of Caledonian Maritime Assets. So I work as part of the vessels team there. And I'm just going to give a very, very quick introduction before I pass over to Richard from the Aquila Braemar LLC group. He'll get into the good stuff. And I was hoping to be there in person, present a little more, but fortunately, I'm confined to the house at the moment, recovering from appendicitis, which is a bit frustrating, but all good. So CMAL are owned by the Scottish Government. We've got 37 vessels, 32 of those operate on the west coast under CalMac Ferries Limited. We've also got a further 5 on the Northern Isles routes, and these operate with Northlink ferries. CMAL have been looking towards alternate fuels for more than a decade now, and that started off with our diesel-electric hybrid battery ferries, which at the time were the world's first. We've also got 2 dual-fuel LNG ferries currently under construction, and we've also we're looking at fully electric ferries as well as part of our small vessel replacement program, which is going to replace 7 small ferries over the next 5 to 6 years. So CMAL, we've also been part of the HySeas group going back to HySeas I in 2014. And as part of HySeas III, we've been working alongside our partners within the consortium and also our consultants on this, Aquila Braemar LLC, or ABL, and they've been helping us with the specifics to develop a concept design for a hydrogen-fueled passenger ferry. And that's for the Kirkwall to Shappensea route in Orkney, which is approximately a 25-minute crossing, and it would help to use up the curtailed wind energy that they have on the island by using a hydrogen electrolyzer to produce the hydrogen. So we've also tried to ensure that, as well as meeting the Kirkwall to Shappensea route, that the design can also be used on other routes around Scotland as we look towards the future and decreasing emissions. That all feeds into the emissions reduction targets Scotland Act in 2019 that was produced. So where we're at just now, we're currently completing the design of the vessel, and we'll produce a vessel tender specification as part of our work package for HySeas. And we'll then look towards Transport Scotland and the Scottish Government for funding of such a vessel. So not very much else to say, so with that I'll pass over you to Richard from LLC, and he'll take you through the design aspects of the vessel so far and some of the safety challenges that we've faced. So thank you, and over to you, Richard.
Thank you, Declan. Yeah, good afternoon all. My name's Richard Featherstone. I'm a naval architect with ABL, Longitude. So Longitude is the engineering arm of ABL. So involved in many different markets. My own speciality is naval architecture, but we have structural and marine engineers as well. Yeah, spread throughout the world. So yeah, just a bit of background on us. So Declan has already covered some of the aspects of the vessel design project. So today I'm just going to talk more about the design process rather than the specifics of the design and how we are trying to produce a safe design and some of the challenges that we're facing with that. We're not at the end of it yet, but we're still working through it. So I'm going to start talking about the requirements and how we've gone through a roadmap to achieve approval in principle, some of the issues we faced, HAZID, particular areas of concern, and some of the specialist analysis that we've had to undertake to prove that this is a safe design. So really, as Declan said, it's a double-ended ferry to operate on the Shappensea to Kirkwall route up in the Orkney Islands. Capacity is for 120 passengers, 16 cars or 2 heavy goods vehicles, and the objective is zero emission operation, so using hydrogen fuel cells and or batteries. So that was the statement of requirements. And then from that, we've produced a concept design. So the principal particulars there on the right-hand side. So there's particular limitations on length overall and beam due to the shore infrastructure, and similarly with depth and draft. wanted it to be efficient and highly manoeuvrable to reduce the amount of time spent manoeuvring. So that drives us down the route of Voigt-Schneider propulsion. And again, as I say before, we did look, like was looked at earlier, a single-ended design, but so a double-ended design would be far more efficient, less time in manoeuvring in and out of port. So yeah, the propulsion system concept. Fuel cells were requested by the client from the start. So we're storing the hydrogen as compressed hydrogen into 10 tanks with carbon fibre. The hydrogen will be bunkered from a pier in Kirkwall. There are 2 locations on the ship where the hydrogen will be bunkered to. And then fuel cell type, we've spoken quite a bit already about the various types of fuel cell ballard AC wave. This particular project is agnostic in terms of we're trying to design for any future fuel cell because this design could be used anywhere. Also, due to government procurement rules, we can't specify one particular type. In terms of numbers, it's designed for 2, but could take 3, and that obviously depends on the size and capacity of a fuel cell. And the driving element is the achieving the speed, which is 9.5 knots with a 15% sea margin. And then on top of the fuel cells, we've also got an energy storage system or batteries, which are provided in 2 banks. So that provides load shaving, range extension, and also return support in the event of failure of the fuel cell system. So here are some of the initial renderings. So it's in many ways it's relatively conventional double-ended ferry design. Many versions like this in the Highlands and Islands of Scotland. But obviously what makes it unique and what's been the challenge has been the integration of the hydrogen system. And that's really what I'm mainly going to be talking about today. So if we take a look at the general arrangement, so this is a view below the main deck. So the main deck height on this is very limited to only 2.5 metres, and that's due to the shore infrastructure. So it's very, very tight underneath there, not much space really. General arrangement kind of indicates there's more space there than there actually will be when you see this thing in 3 dimensions. But essentially, we've got the bit where we're really interested is in the middle, the fuel cell room. So we've got 2 fuel cell space claims, and then we've got a further space for an additional one if we require. And that space is accessed through the switchboard room via an airlock. And it's our assumption that the fuel cell room will be hazardous, although I appreciate with the FC wave that the fuel cell itself is the hazardous zone. In the port forward and starboard aft quarters, you've got 2 battery rooms, and then adjacent to those, you've got the 2 thruster spaces, and then the only other room of interest really is the plant room, where there's general ship systems stored. So this is really what drives the dimensions of the vessel. Obviously, there's limitations on length and beam. It's the requirement to get the number of cars in there and the spacing required between those cars, the size of the passenger lounge, disabled access, and so on, that takes you up to an 11.5 metre beam, which is almost the limit once you take into the fenders, so into account the fenders. So it's the cargo, if you like, and the passengers which have driven the dimensions that we've got, and this is the probably key slide. So one of the first ideas that we had would be that we wanted to separate the passengers from the hydrogen systems as far as possible. So on the starboard side, which is side nearest to us, so this is a double-ended ferry, you have the passenger lounge. And on the port side, you have the bunkering for the low-level bunkering for the hydrogen system. You have access to the fuel cell space. You have the ventilation trunks up from fuel cell space. So we try to keep passengers and fuel cell equipment separate from the outset. And the upper deck, there's capacity there for people to go on the upper deck in when the weather permits, and in the summer seasons there's large variations in passenger numbers, so can take up to 120. And on the port side you have a small crew mess, and that's just a view of it in elevation.
I would just say something on the emergency generator.
So
we've
yeah,
got one.
so yeah, the emergency generator is located on the starboard side. So originally we were looking at an emergency generator that would provide full return to port capabilities. That was a nice to have. We're not now doing that. The emergency generator will be as per the SOLAS requirements, and emergency power will be provided, or return to port will just be provided on the batteries. So here is took a section, midship section, and plan on the bridge deck, and this has kind of been the crux or the most complicated aspect of the vessel. So, and I'll talk about it a lot more as we go along, but in terms of the hydrogen storage, where do you put hydrogen on a vessel like this? There's not many places, and I'll talk about the thought processes that we went through to arrive where we are. But this is where we are. So you have an offset bridge onto the starboard side, and then sort of port area you have the banks of hydrogen tanks. And then also on that same area you have the upper bunkering station. So this vessel has two bunkering stations. There's a lower one on the main deck and an upper one on the upper bridge deck. So the objective of this project, as was given to us by CMAL, was that they would like a design that is approved in principle, so that at the end of it they could go out to tender to a shipyard that could develop a basic design with no real showstoppers regarding the hydrogen system. And so this is sort of a bit of a flow diagram of how we've got there. So we had the initial client's requirements, which we've spoken about, and from that we've developed a concept design, and that's been all the things you'd expect in a concept design, so general arrangement, weight, stability, resistance, initial systems design. We review that design weekly, so we have a client meeting weekly, so we go through the key issues in the system, the ship systems and so on. And that's worked really well, so being able to mature the design reasonably well with that. But then early on we also needed to start talking to the flag. It's going to be a UK flagged vessel, so the Maritime and Coast Guard Agency, and also class. In this case it's DNV. And the reason for DNV was its experience with the Hydra in Norway, and also the DNV hydrogen handbook, so there's the expertise there. So from that we wanted to know what the approval alternative design route was to achieve approval in principle, what we needed to do to achieve that. So there was the major activity there was to hold a HAZID, which we held in January of this year. And then in parallel to that, DNV produced a list of requirements that documentation that they would need to see in order to grant approval in principle. So there are those various documents and drawings there. But in addition to that, we required specialist analysis because we are ship designers. We have some CFD capability for resistance and propulsion, things like that. However, and I'll come to it later, there was a requirement to carry out fire and explosion analyses, vent heat radiation studies and so on, which is outside our capability. So that was that's a scope of work that we've had to subcontract. And then that feeds all back into the concept design. So there's been revisions to that based upon that feedback that we've got. That study is still ongoing. So it's our hope that once that study is complete, we'll be able to complete the outstanding details in the concept design, such as updates of system P&IDs and general arrangement, and submit those and achieve approval in principle. So that's our roadmap, if you like, and what we wanted to achieve and how we're going to achieve it. Now, the first thing that problem we come to with a hydrogen vessel is the regulatory framework, or probably should say lack of it. As a passenger vessel, the principal requirements are given by the EU passenger ship rules, and this is a Class C passenger vessel, which is 2.5 metre significant wave height, probability of 10%, 15 miles from shore. It's a relatively inshore vessel. So a lot of the overarching requirements are given by that legislation rather than SOLAS. So a lot of it is drawn from SOLAS. And then also for the gas system is referenced to the IMO IGF code, International Code for Gas Fueled Ships. And then there are also DNV rules for fuel cells. But then we come to the regulatory gaps. So at the moment, there are no specific IMO rules for hydrogen as a marine fuel. The IGF code has prescriptive requirements in there in terms of developing your hazardous zones and so on, but they're based upon LNG or LPG, so they're not really applicable to hydrogen, which behaves in a very different way. And similarly, there are DNV rules for compressed natural gas, which are good reference, but limited applicability. The main sort of guidance would be the DNV book for hydrogen fuel vessels, which is a very useful guidebook. Having said that, the IGF code has got prescriptive requirements which are not applicable to us. What is important is that you achieve the functional requirements of the IGF code, which is basically achieving safety equivalent oil fuel systems, restriction of hazardous areas, and so on. And the second thing is the general requirements in there. And this is really the key output from the HAZID, was that the design has to limit the explosive consequences. So that, in terms of damage to the ship, to crew, to life-saving equipment, and so on, it has to be demonstrated that your design can achieve those general requirements. So unlike, say, an LNG fuel ship, where you know that if you provide a certain hazardous area from the tanks, or if you have a certain distance of the doors from the front of the wheelhouse and so on, you're going to achieve the requirements. With this, it wasn't clear because obviously there's no specific rules for hydrogen. So these are some of the issues that, for us as designers, that we faced. So, as I talked about, goal-based prescriptive requirements are easier to design against when you've got a certain distance of a hazardous zone, and you know what you can put near there and so on. That's easy to work with. When you don't have that, it's a bit more difficult. So that leads to a lot of ambiguity in the arrangement of the ship. One of the other things as well is, at the moment, is that industry knowledge is still developing, so limited, but it is developing, and so there's not that experience that you would have with other propulsion methods. And also, it's the early reliance on specialist subcontractors, such as the CFD work, which for a conventional vessel you wouldn't need to do, and it's additional time and cost to produce a concept design. And also sometimes there's been conflicts between what it says in the IGF code and what's happened in reality, and there's stream test and HAZID. So as a bit of a regulatory framework that we've kind of created ourselves, was our starting point was to create a basis of design. It's a really useful document. So a basis of design essentially lists all the standards that you think you can apply and how you can apply them, what the limitations of those are, and what those general design principles are. So obviously the principal piece of legislation that we're interested in is the passenger ship safety. So from that we have two routes. So on the right hand side here, in the green, you have sort of the established regulatory routes that you would use for any ship. Class rules, IMO, which cover, ship systems, stability, load line, structural strength, and so on. On the left-hand side, we're following an alternative design process, which has got many references and is described by several documents. The main one being the MSC 1455, and also within the DNV Hydrogen Handbook. So the scope for the approval in principle is not the whole vessel, it's the hydrogen system. And the thought is that the not to say not challenging, but elements such as the stability, structural strength, and so on, we can produce those against the rules, demonstrate compliance, and then when we move on to the basic design phase, approval from either flag or class will be relatively straightforward. However, with the hydrogen systems, we needed to get approval in principle for those first. So in terms of the systems that we're looking at, it was the bunkering, it was the supply, the ventilation, purging, and the inerting. And then also was the systems which interface with those, just fire detection, alarm, build system, and so on. And if all goes well, they'll be granted approval in principle, and then we will move on next to engagement with UK flag within the basic design phase. So that's kind of an overview of the process that we're looking at, which we've developed and worked with. So talk about the alternative design route. So this is not using established prescriptive routes such as in SOAS or so on. So the start point for that was a discussion between the Maritime Coast Guard Agency and DNV as to who was going to take the lead on that. MCA weren't able to provide any sort of approval for the design, so DNV took the lead, whereas the MCA took a kind of a backseat. They watched what happened and offered clarifications and guidance. So the first activity in this route was the HAZID, which we had in January this year. Had three main objectives, and the first one is the most important, was to identify any showstoppers. If there's anything in the current design that stops it dead, and as it was, there was one major showstopper, and that was come on to it. So that's the general description. Was the location of the hydrogen tanks. So they know in all there's 41 hazards identified. 42 recommendations, but the showstopper was the location of the hydrogen tanks, and that could we demonstrate compliance with those general requirements of the IGF code. And the concern is that we position the tanks very close to the wheelhouse. There's obviously increased risks of danger to the operators of the vessel, both in their place of work and could they get to life-saving appliances. So going back to the prescriptive requirements of the IGF code, is where are we not allowed to put tanks? So it doesn't leave many places on a vessel like this you can put them. So you're not allowed to put them anywhere within BF5, so within 20% of the beam. So that takes out quite a portion of the vessel. You're not allowed to put it within the 4.5 extent as shown on there, and also there's a restriction on deck. So the locations kind of left with are below the main deck, on the vehicle deck, which is not good because you want to put cars there, or the bridge deck. So really we were left with one choice, which was well, two choices, which was below the decks or on bridge deck. So we looked at putting the tanks below the main deck, and had some very major concerns with that. Firstly was that the required size of the tanks, the volume, there was not going to be any room for inspection or maintenance. Very, very tight. Also, if there was any leaks, it would tend to gather around stiffness and so on. Added to that was that once, we'd fully defined all the systems that need to be on board, there really wasn't enough room below deck for this anyway. So our choice was to position the tanks on the bridge deck. So that's a bit of a description of all the other places that we looked at which weren't appropriate. So following the HAZID, we had a little bit of a move around in the tanks. We kept them within the B05 damage line. We've moved them slightly aft, and the reason for that was to increase the distance of the hazardous area from the tank connections to the wheelhouse door. But nevertheless, there were three items that we needed to go out after the HAZID and do further work on, and that's what we got the specialists in to do, which was the vent heat dispersion analysis, the dispersion of hazardous gases through the vent, and a fire and explosion risk analysis. And as I say, for that we needed to go to a specialist, and that specialist is a company called Gexcon. We're based in UK, but all over. And so from that, we had to agree what were reasonable scenarios that we could look at for release and explosion. So came up with five different scenarios. So just going back a couple of slides. You'll see on the rendering, you've got the banks of tanks, and there's a blast wall around it, and then the white pole is a space claim for a vent mast. Now we're not fully defined at the moment as in terms of the size, but we know the height's going to be about 10 meters. So the first two scenarios were what happens if there's a pressure relief valve releases either one tank or all 10 tanks up the vent mast, and that's ignited. What happens? The following three were all about ruptures of the bunkering line actually going into the tanks themselves. And here's the criteria. So criteria for thermal radiation exposure. So I kind of color coded these so they will relate to the diagrams you'll see on the next few slides. But obviously you don't want to be getting the orange or the dark blues. And then agreed a few points of interest. So the upper bunkering station, the hydrogen tanks around the blast wall. And the objective that we wanted to get out of this study was really what do we need to do regarding a blast wall and the height of the vent mast. So that's the work we've given to Gexcon. Now that work is still ongoing, so we're not at a point yet where we can give that information out as to what the outcome of that has been. But they have carried out some of the work regarding the ignition from the vent masts. So the first one is looking at ignition of a single tank venting out through the mast. Second one, as you can see, that's all 10. Third one is, in all cases, we're looking at a worst case scenario of the wind blowing onto the wheelhouse. So we're getting quite high radiation there. So, this is going to help us design the blast wall and the thermal insulation for it. So yeah, these are the various scenarios, and then this here is looking at the probability of that bunkering line becoming ignited. What happens if there's a 50% probability of flame occurrence, and at that height is the height that they would recommend for the blast wall. But as I say, this work is still ongoing. So sorry. And so yeah, as I say, this work is still ongoing. We're expecting it probably later this month. And as I say, the outcome of that will be general comment on the layout of those tanks, size of the blast wall required, the height of the vent mast, and so on. And the final slide really is the deliverables that we need to provide to achieve this approval in principle. So as you can see, there's quite a lot of work that goes into producing a concept design for a hydrogen vessel at the moment. A lot of upfront work at a concept stage. Quite difficult for a designer to produce a safe design initially without the involvement of many others. So it's been quite an enjoyable but complex learning process. So that's really what I wanted to get across today. So yeah, that's me.
Thank you very much, Richard. We have time now just for probably about one question before our next speaker, because he has to get away after his section. So Maxim's got his hand up quickly. Maxim, please.
Yes, thank you. A lot of your analysis relies on mostly about the hydrogen storage, but what about the line feeding into the fuel cell? It's quite a long way going 2 levels down to the fuel cell location. Yes, and there will be inevitably leak points along that. And yes, have you thought about monitoring of that line on any ventilation along the way?
Yes, that's right. So so there's a duct that leads from the hydrogen tanks down to the fuel cell space. That duct will be ventilated. The pipes will be double walled, and there'll be monitoring of pressure on that pipe. So yeah, that was one of the recommendations in the HAZID, was the design of that duct.
Thank you.
One fast question, Richard. Yeah, now you're talking about the duct. If the duct was tight, did you then need the double wall pipe? Could the duct have been a secondary enclosure on the pipe? Just a question.
I'm not sure. In terms of the position of the ducts, again, going back to the IGF code, there are restrictions on how close you can run the piping to the ship side. So that's 800 millimeters. And then on the other side, you have the vehicle deck. So one of the things that we also want to prevent was vehicular damage of the pipes. So to put them inside a steel duct seems to be safe.
Yeah, but could the duct have prevented that you need to run in double wall pipe?
I'm not sure.
Just very quickly, I think Monica or Hans-Jürgen, would you be able to answer that from DNV?
Yes, should you please repeat the question?
So the question is, there's double wall pipe running in the ducts.
Yeah.
And I think the question is whether could that be single wall pipe and the duct acts as the remaining as granular space?
Yeah, no, we are at the moment recommending to have the double wall pipe as the best solution because the inter-barrier space in the double wall pipe will be smaller, and say as to have a small space to collect the leaks is best, and then you will have a kind of double barrier once you have the double wall pipe. And in addition to that, you have the duct that, as mentioned by Richard, will protect from mechanical damage, but also will be a, say, gas-tight duct that will be ventilated and have gas detection, and so it will be somehow a double barrier on that pipe. And because of the, I mean, the hazards that are known to happen if you have a leak in an enclosed space in the ship, then is somehow an item where it's better not to take a risk.
Thank you very much for
Okay.
answering it such short notice.
Yes. Okay, thank you.